Hello everybody, welcome to another video, a calculus video. This time we are going to talk about vectors and directional derivatives. Before we about vectors, let's look at points. We'll compare and contrast points and vectors. And points are dots basically, while vectors are directional line segments denoted by this symbol. So points, we say if there is a point A and B, points are denoted by coordinates A1, A2 so far if it's two-dimensional, and B1, B2 if it's two-dimensional again. But vectors are special things. We say P, if P is a vector, it's denoted by these brackets, brackets that are like pointy brackets, and you can write it as P1, P2. That would be a vector P1, P2, just like points are denoted by two values in two dimensions. Vectors are denoted by two scalar values in two dimensions. And we can write Q as Q1 and Q2. But Q and P are line segments, they are not points, line segments. So we have the vectors as something that points don't have. Vectors have magnitudes and directions. We'll talk about the magnitude and the direction soon, but first let's look at vector P. Let's say this is P, denoted by P1, P2, it's a directed line segment, and this is Q, directed line segment, denoted by Q1, Q2. So, if we have a vector U that goes from P, that connects P and Q, that goes from P to Q, so from P to Q is known as U, vector U is given by vectors again, Q1 minus Q2 and, Q1 minus P1. So let me erase that P1 minus Q1. This is P to Q is Q1 minus P1 and Q2 minus P2. That's how you denote the vector U that goes from P to Q. Q is written first and P second. So the next thing we want to show is the angle, the direction or the angle. So if P makes an angle alpha, let's say, P makes an angle alpha with the x-axis, then tan alpha would be equal to P2 over P1. That's the alpha. It would be the opposite over the run. So if theta was the angle that Q made with the x-axis, it looks like Q. So tan theta is equal to Q2 over Q1. That's the direction. Now let's look at the magnitude. Magnitude of P would be, we denote it by vector P, we denote it with two lines to show magnitude is equal to square root of P1 squared plus P2 squared. And magnitude of Q would be square root of Q1 squared plus Q2 squared. So that's the magnitude. So we talked about the direction of the vector and we talked about the magnitude. The next thing we'll talk about unit vector. So let's say this is a unit vector. A unit vector of q, will denote it by a q hat, is equal to, we know that q, vector q is given by q1, q2, then the unit vector q is equal to q1 over square root, the magnitude, in fact q1 squared plus q2 squared, and q2 is over square root of q1 squared plus q2 squared. That is the unit vector. Similarly, if P is P1, P2 is denoted by P1, P2. So P, the unit vector of P would be P1 over square the magnitude P1 squared plus P2 squared, comma P2 over square root of P1 squared plus P2 squared. So that's the P vector right there, the unit vector of P and Q. We'll look at the vectors a little further. Let's say we have a vector V, which is denoted by P and Q. Then if K is a constant or a scalar, KV would be KP will be denoted by KQ. Similarly, and if you add these two vectors, if you say, I want to see what vector V plus KV would be represented by, it would be P plus KP, Q plus KQ. And if we denote vector U as R and S, then vector U of V plus U would be, they're both vectors, would be P plus R, comma, Q plus S. So all we did here is we took the value on the left side of the comma and we put it here, added them and put it here, and we took the values right side of the comma and we added it and put it here. Same thing happened here as well. We took P and KP and added them. Then we put Q and KQ and added those two values. So next thing we want to do is we want to denote the dot products. So if we take we should erase that. We will say if we want to get the dot product, let me put a line across, and if we say v dot u, the dot product is always a scalar. So we do not put the pointy brackets, we use normal brackets. So v dot u would be P R plus QS, which is a scalar value. Now let's look at the dot product of V dot KB. So that will be P times KP plus Q times KQ. So that would be Kp squared plus Kq squared. So that would be a scalar product. Let's do one more dot product. Let's say U is equal to, say V is equal to, it's a multidimensional vector, not just two values, it's denoted in 4 dimensions. It would be V1, V2, V3 and V4 in 4 dimensions. And let's say U is equal to U1, U2, U3 and U4. So v dot u would be v1 u1 plus v2 u2 plus v3 u3 plus v4 u4. That would be the dot product. And sorry, this shouldn't be pointy brackets. It should be normal brackets because it's a scalar. So this would be also circular brackets because it's a scalar value. So given, let's say we go back to our previous definition of U equals R and S, and if V is equal to a line to separate them, V is equal to um, P and Q. Then if we want to get let's look at the dot product first. U dot V is equal to, its curly brackets, just normal brackets, RP plus SQ. That's R times P plus S multiplied by Q. But if you want to get the angle between V and U, let's say the angle between V and U is theta. So we can write it as cos theta is equal to the dot product between V and U over the magnitude of U and magnitude of V. So we know the dot product is a scalar. And when we know the magnitudes are scalar as well. So let me remind you what the magnitude of U would be. Magnitude of U would be R square root of R squared plus S squared. Magnitude of V would be square root of P squared plus Q squared. So that would be the magnitude, and the dot product would give you a scalar value as well. So you can get the angle between the vectors, the cos of the angle between the vectors. So the question is, we need to find the directional derivative of fxy, which is a two-dimensional function equal to x squared 2x squared plus y squared at the point 1 1 in the direction of the vector 3 minus 4. Now since we are given a vector, we need to find, what we can find here is the magnitude of the vector. So if we find the magnitude of the vector u would be equal to 3 squared plus minus 4 squared square root of it, that is square root of 9 plus 16, which is equal to 5. So then next thing we can find is a unit vector. The unit vector is it's also vector 3 over square root, sorry, 3 over 5, not square root, 3 over 5, because we have already found the magnitude, and it's minus 4 over 5, and this is a vector. So next thing we need to do is find the directional derivative of f with respect to, with directional derivative of f in the direction of the unit vector u. That's what we need to find. And we found that the unit vector u is, we know the unit vector already. Let me replace the unit vector here. So the unit vector is 3 over 5, comma, minus 4 over 5. So directional derivative could be written, and this is written as gradient grad f dot u. So this grad f is partial derivative with respect to x f, that's a vector, and with respect to y, and we multiply, we do the dot product with the vector u, which actually the unit vector u. So let's look at the partial derivative of f with respect to x when you take the partial derivative of f, this is your f with respect to x, you get 4x. Partial derivative of f with respect to y, you get 2y. And then you multiply it by, take the dot product with u. So that is 3 over 5 minus 4 over 5. So when you multiply this, you get, just a second, you get, this is of course a scalar value because we know dot products of two vectors are scalar values. So we get 12 over 5x, comma, minus 8 over 5y. We must remember to always this should be plus. Always use the negative values. Do not drop off the negative values. So we need to have that. So if you go back to the question, we are asked to find the directional derivative at the unit vector. We have done that already. Minus 4, 5 of f at 1, 1. That's what we are supposed to find. So the next thing we need to do is just substitute x as 1, y as 1. So then we get 12 over 5 minus 8 over 5. So it's actually 4 over 5. That's the answer. So what this gives you is the directional vector or the directional direction at 1, 1. That's what you get of this function 2x squared plus y squared.